Last time I told you about stable isotopes and how they're fractionated by biological processes. But it turns out that stable isotopes of carbon are not only fractionated by life, but also by burial and erosion. I tend to think of isotope ratios as just that. They're the ratio of the heavier isotope, in this case carbon-13, over the lighter one, carbon-12. If something has relatively more carbon-13 than carbon-12, it will have a larger carbon isotope ratio, which is also described as a positive ratio. That's because the top of the ratio is bigger number than the bottom of the ratio. If the amount of carbon-12 increases relative to carbon-13, the ratio becomes smaller and therefore more negative. In fact, the carbon isotope ratio is a bit more complex than that, since we have to standardize the ratio to the amount of different isotopes in the biosphere. But the basic idea is right. So, if there is an increased burial of total organic carbon that is loaded with carbon-12, the ratio of carbon in the biosphere will increase because there is now less carbon-12 in circulation in the biosphere than carbon-13. We describe this change as a shift in the carbon isotope ratio of the biosphere's whole carbon reservoir. This is a very important concept that we will repeatedly turn to in this class, so pay attention. The isotopic shift occurs because total organic carbon burial of carbon-12 removes carbon-12 fixed by plants and animals from the Earth's surface into sediments. We know this buried organic matter is things like coal and oil and organic-rich rocks. As a result of burial, the organic and the carbonate carbon that remains in living organisms in the biosphere will develop a more positive carbon isotope ratio as more and more carbon-12 is buried. Conversely, erosion of organic carbon reintroduces carbon-12 back into the biosphere and shifts the global reservoirs towards more negative carbon isotope ratios. These changes in the amount of carbon buried over time produce what's called a reservoir effect because of changes in the amount of organic matter buried in geologic reservoirs or eroded and put back into the surface biosphere reservoir. Okay, so here's an M&M analogy. If you have a bowl of M&Ms and prefer a certain color over another color, the number, say, of blue M&Ms that you pull out will be a function of both how much you prefer it and basically how many you remove from the given jar that you've started off with. You're fractionating the M&M supply that remains in the bowl by preferentially selecting the blue ones. If blue M&Ms are highly fractionated because you like to eat them, the remaining M&Ms will be depleted in your favorite color. To take the analogy farther, if you have another bowl full of blue M&Ms and you add all of them back to the first bowl, you will have emptied the blue reservoir from the first bowl and greatly changed the composition of the other bowl in terms of its abundance of blue M&Ms. Now just think of the different M&M colors as isotopes of carbon, and you have basically the right analogy. Now all this isotope stuff is important because we can use the carbon isotope ratio of organic matter or the carbon in carbonate, like calcium carbonate, to monitor how much organic matter is being buried or exhumed on Earth. For example, we will get to this in a couple of weeks, is the snowball Earth events. There's a series of times where we have observations that suggest that Earth's oceans became substantially frozen over. During snowball Earth events, carbon isotopes shift dramatically from plus 10 per mil to minus 10 per mil and back again. How do we interpret this? Well, if the burial of organic matter removes carbon-12 from the biosphere into sedimentary rocks, then the remaining organic carbon isotope ratio for the rest of the biosphere will shift increasingly towards positive values. The reverse is true as well. If organic matter loaded with carbon-12 is eroded out of sediments and put back into the biosphere, the Earth's overall carbon isotope ratio will become more negative. So, the plus 10 per mil to minus 10 per mil shift seen at the start of snowball Earth must indicate the erosion of organic matter on a massive scale, putting carbon-12 back into the biosphere. And that's probably done by glacial erosion of previously buried organic matter. Eventually, after the ice melts, organisms again start to produce lots of organic matter, and when it is buried, the carbon-isotope ratio shifts slowly back towards more positive ratios, as more carbon-12 is buried and removed from the biosphere. So that's the basics of carbon isotopes. We'll return to this topic numerous times in class.